0, 1, 2, 3. Let's get started.
Real good.
Hello, my name is Devin Ellington, and this is my tracking pan tilt. Directional antennas such as this offer superior range and signal strength compared to their omnidirectional counterparts such as this. However, one downside of a directional antenna is that they require precise aiming at a target in order to take advantage of all of their benefits. When communicating with a moving node, repositioning the directional antenna is not only difficult but very impractical. This device here solves that solution by automating the entire aiming process. Let me show you how it works. Radio 1 is moving in the distance. As it moves, it transmits GPS data via 915 MHz, allocated by the FCC. Radio 2 receives and acknowledges the reception of said data. The data is then output via serial USB to a computer. The computer calculates the Haversine formula, which calculates the shortest distance between 2 points on a sphere, in this case that is Earth. That information is output via serial to the first Arduino, which is used to control the azimuth and elevation of a pan tilt. This pan tilt is connected to a directional antenna called a Yagi, which is targeting radio number 1. The coax of the Yagi antenna is connected to radio number 2. This allows the tracking pan tilt to continuously monitor and follow the GPS location transmitted by radio number 1. The parts used included 2 Arduino Nanos, 2 TMC 2209 stepper drivers, 2 NEMA 17 stepper motors, 1 I2C multiplexer, 2 AS5600 magnetic encoders, 2 LCM I2C interfaces, 2 LCD displays, 1 12-bit RGB ring, 1 rotary encoder, 2 1K ohm resistors, 2 100 microfarad 50 volt capacitors, 1 12 volt 5 amp DC power adapter, and 2 5 volt USB-C data cables. The radio requirements included 2 NRF52 microcontrollers with compatible LoRa radio modules, 1 L76K GNSS module, 1 computer, and a directional antenna. Now that we've discussed what components are used in the project, let me show you where each is utilized. A rotary encoder acts as the user input with a joined RGB LED status indicator. 2 displays can show critical information to the operator. The display on the left is an informational dashboard at all times. The display on the right is menu and instructions for the user. The rear of each motor is equipped with a magnetic encoder with a bipolar magnet. This allows us to know absolute position at all times while the device is powered. 2 stepper motors provide the ability to change azimuth and elevation. Following the LCD instructions, we can press the encoder to start. We can level to the north and confirm. This information is now set for the rest of this session. It is now tracking the location of the node where it thinks it is. For this demonstration, our fixed location for the pan tilt is set a few miles away so that we can track our location instead. As seen on the bigger LCD display, we know whether or not we have locked onto the target within 2 degrees, the distance from that target in meters, and we also know the target and actual azimuth and the target and actual elevation as well. Other options include force stop. We can also manually adjust the azimuth and elevation for specific needs. Here we can adjust the azimuth. As you can see, we can also switch to elevation as well. Thank you for watching.